Okay guys, time for my favorite lesson. I couldn't give it up, so I decided to make a video. Today we're going to talk about trig identities. So remember from yesterday's lesson, right at the end there, I was talking about the difference between an identity and an equation. So an equation has a variable in it, and I'm just going to add a new page here so we can talk about this for a second. An equation has a variable in it, and it could be something like 2x plus 5 equals 15, right? And this has a solution. There are some numbers for x that will make this statement true, and there are other numbers for x that will make this statement false. So for instance, if I pick x is equal to 5, then this statement is true. But if I were to pick x equals 7, then my left side would equal 14 plus 5, or 19, and my right side would equal 15. So that would mean that my left side does not equal my right side, and this is not a true statement. And this is going to happen for an equation. Some numbers, like x equals 5, so here I would get the left side is equal to 2 times 5 is 10, and 10 plus 5 is 15. And I would get the right side is equal to 15, and there I'm getting that the left side is equal to the right side. So sometimes for an equation, when I pick a number, I get a true statement, and sometimes when I pick a number, I get a false statement. That's not the same for an identity. So yesterday I kind of gave you a silly one for your identity. There's lots of different ways that we can come up with identities, but they don't have to have trigonometry in them. So we are going to be focusing in this chapter just on trigonometry ones, but I could make one up. Like yesterday, I gave you the example of, I think I gave you x squared or 3x squared is equal to 18x cubed over 6x. This is an identity, and what that means is no matter what number you pick for x, the left side will equal the right side. The only exception in this case, because I do have a denominator with an x in it, is that x cannot equal 0. So there is one exception, and that's just because it's not in our domain. But otherwise, this is true for all values of x. So I could pick x is 1,067,500 and plug that into the left side and plug it into the right side, and they would both give me the same answers. Now, it's exhausting to go through all the possible numbers that you could plug in here, and you can't. There's an infinite number of numbers. So you could never prove to me for sure that it was an identity just by picking numbers and plugging them in. You would have to change the left side or the right side so that it looked like the other thing. So our left side is 3x squared, and our right side is 18x cubed plus 6x. So I can't plug in a number and just show that, oh, it works for that number, so it must always work. I actually have to change how one of the sides looks, or sometimes I have to change both. So yesterday in class I said I can divide the coefficients here. 18 divided by 6 gives me 3, and then I can subtract the coefficients, or sorry, the exponents on x, and 3 minus 1 gives me 3x squared. So I can see now that really the right-hand side does look exactly like the left-hand side, and therefore this is an identity. It means it's always true no matter what number I put in for x. Another way to check identities versus equations is to, hold on here, we'll go to Desmos, and we can type in the left-hand side and the right-hand side. So in my first example, my left side was 2x plus 5, and my left-hand side was 15. Type in y equals 15. And when I pull out here, you can see that my blue graph is just a horizontal line across 15, and my red graph is a diagonal line. So yes, they do cross at x equals 5. They do have an intersection point, but they're definitely not the same graph. So this is not an identity, it's an equation. On the other hand, when I look at my other equation, it was 3x squared on the one side, and on the other side I had 18x cubed over 6x. And what you notice here, I'm going to get rid of those lines so that it's not all crowded. What you notice here is that the orange graph goes right on top of the green graph. So right now I'm looking at the green graph of 3x squared, and when I click the orange, it goes right on top, which shows me that this is an identity. It's true for every number of x, so no matter how far I zoom out, no matter which x values I plug in here, I am going to find that they give me the same answer. So that's how I know it's an identity. So going back to our lesson, here we are. 5.5 trig identities. So an identity is a statement that is true for all values of the given variables. That means that the left side equals the right side no matter what value you put in. Don't forget that whenever I have a fraction, though, on the left side or the right side, the denominators can't be 0. So I have to state restrictions, kind of like we did in our rational functions unit. So we have some basic identities, so things that we just accept to be true. These are identities that are proved in the textbook on page 305. So if you want to take a look at those proofs, you can. I'll talk about the proofs next week and why we know these things are true. But for now, you just get to accept that these are identities and they are always true statements. There are 3 different types of identities that we have. The first one is our quotient identity. And our quotient identity tells me that tan x is the same as sine x over cos x. This is true. So you could take any number for x, plug it into the left side, write down your answer, and then take that same number for x, plug it into the right side, and your answer would be the same. I can also see that on Desmos. So if I go back to Desmos and I type in tan x, I've zoomed out way too far here. Let's go back home. There's tan x. And then if I type in sine x over cos x, you can see that that graph ended up right on top. Even though it's like a weird graph, the graph is right on top of the other one. So that's how I know it's an identity, and I can prove that to you algebraically next week if you're interested. This is an identity that you are going to memorize. You're just going to accept that this is true. Tan is always equal to sine over cos of the same angle. The next identity that we're going to accept as always being true is that sine squared of an angle plus cos squared of an angle is equal to 1. Now you guys haven't seen this notation yet, so just so you know, what this means when I say sine squared of x is it means find the answer for sine of x and then square it. But instead of me always having to write those brackets, we just put the squared on the sign, and that means take the whole thing and square it. So again, I can go over to Desmos and show you that this is always going to be true. If you take the sine x and you square it, you take the cos x and you square it, and then add them together, it always equals 1, no matter what x number you put in. So first I'm going to type in the right-hand side this time so you can see the 1 line. There it is, going across at 1. And then we'll type in my left-hand side, which we said was going to be sine of x all squared plus cos of x all squared. And take a look, that red graph went right on top of the blue graph. That's kind of weird and crazy. And you can try it in your calculator if you want. Pick any number for x and plug it in here. So you could pick like negative 4.5, right? You could pick any of these x values here. So here I've got negative 3.55. I could pick any of those x numbers and plug it into that equation, and it actually comes out as the answer is 1. And again, I can talk to you about why that's true algebraically next week. For now, you're just going to accept that this is always true. I'm going to just erase this now. Make sure you've made a note somewhere so you know what that notation means. Now, if I'm accepting that this is true, sometimes it's handy to be able to rearrange this equation. So that means that sometimes I want this to look like cos squared of x equals some stuff. And in order to do that, what I'm going to do is just take that sine squared x and subtract it from both sides. That means it's going to go away from this side. And on the right-hand side, I'll get 1 minus sine squared x. So if that first blue line is true, then this second line also always has to be true. I could also rearrange it so it looks like sine squared x equals. That means I want to get the sine squared x alone in the first version, So instead of adding cos squared x to both, or sorry, instead of adding cos squared x on the left, I'm going to move it over and subtract it from the right-hand side. Now, I would not suggest memorizing these green lines because really they're the same as the blue line. You really just need to memorize that sine squared plus cos squared of x is equal to 1. So our last set of identities here, it is actually a set of 3 for the last one, and you already know these identities. These are our reciprocal identities, and we remember that this means that cosecant of x is equal to 1 over sine x. Secant of x is equal to 1 over cos x, and cotan of x is equal to 1 over tan of x. So you've got 5 equations there in blue that you need to memorize. These are identities that I get to use to rearrange the ones that I'm going to try to prove.